Alrighty, everyone. Final video for this unit. And yeah, it covers a lot, but what's cool is I was really able to condense this down into just some big ideas, okay? So all of these topics really address buffers, okay? And the reason why a solution is called a buffer solution is because it's a solution that is buffered against changes in pH, right? Like a buffer solution resists or slowly changes pH. Like it's resisting any large change to pH. Until it gets overwhelmed, but it really does a good job of like slowly changing or its pH. It doesn't drastically change pH. And there's a couple different ways of making a buffer solution, but the AP Chem questions primarily focus on this one type of buffer solution, and it is when you combine a weak acid and you take that weak acid and you add it to a salt, an ionic salt, but the ionic salt has the conjugate base. So ionic salt with conjugate base. Okay. So if we have a weak acid and we add a ionic salt that contains the conjugate base of this acid, then that's a buffer solution. So here's an example. We know that HNO3, that's a strong acid, but HNO2, that's a weak acid. Now what if we have a weak acid, and if this were to break apart, think about this for a second, you would have H plus and then you'd have NO2 minus. So if we get NO2 minus, if that's part of an ionic compound, like if it's combined with anything from group 1, because all of these metals here, when they're an ion, they have a +1 charge. So we could have like potassium, that's a +1. If that was with NO2 minus, the conjugate base of this acid, then it would make KNO2. There's an ionic salt that it has the conjugate base of this acid. So those two solutions combined would be a buffer solution. And typically the questions that they have is they say, hey, here's this buffer solution, and you usually have to recognize that it's a buffer solution. If we add a little bit of a strong acid, then what would happen to this? And if we add a little bit of a strong base, what would happen to this? So let's look at those two scenarios. So let's add a strong acid, okay? Strong acid. So if we add a strong acid, do you think that strong acid will react with the weak acid, or do you think it's going to react with the conjugate base? Acids react with bases, so strong acids completely break apart into like H plus, like it's floating around, and it's going to react, instead of increasing the pH, what it does is it reacts with the conjugate base, this NO2 minus, but H plus, and it reacts with NO2 minus, guess what it makes? The original weak acid. So if you add a strong acid, the conjugate base that's in the salt just turns it back into more of this guy. And so then the pH doesn't really shift that much. So that's how it's buffering against a change in pH, making the pH lower. But what if we add a strong base? Well, we know that if it's a strong base, what do you think the base is going to react with? Do you think it's going to react with the weak acid, or do you think it's going to react with the conjugate base? A base is probably going to react with the acid. So strong bases, they break apart, so it's just a bunch of OH floating around there. And it's going to react with the weak acid. And what happens is that this base pulls the hydrogen off of that weak acid, and it turns it into just a water molecule. This OH minus stills the H plus from the weak acid and becomes a water molecule, and it leaves over NO2 minus. Oh, well, that's just some more conjugate base. So when we add a strong base, the weak acid reacts with it and turns it just into more of the conjugate base that's already in there. So the pH doesn't really change. And as long as the weak acid is present and the conjugate base is present, then it will resist or buffer against pH changes. Once one of those is gone, then the pH can start drastically changing. Now, remember how we talked about the half equivalence? Like, the equivalence point is somewhere in here, right? Like, that's the equivalence point. And the equivalence point occurred at a volume of 15 milliliters. So half of 15, right? Half of 15, 7.5. So here's 7, so 7.5 is right there. That's the half equivalence. And don't forget that at the half equivalence, the concentration of the acid is equal to the concentration of the conjugate base. Isn't that just a buffer solution? It's an acid, a weak acid, with its conjugate base. And so look at the pH. All through this range, the pH doesn't change very much. We're being buffered against big changes in pH. And it's not until one of these things, in this case the acid, runs out that we start seeing this drastic change in pH. So this area is the buffer area of a titration curve, okay? So if they ask you, hey, which portion of the curve are we seeing a buffer reaction or is buffering against changes in pH? It's that portion of the titration curve. Okay, scary buffer questions are not as scary as they look. It looks terrifying, but if you can identify what the items are, it's really not so bad. The question itself, if we skip to the bottom, it says, the data from the experiment are given in the table to the right. Which of the following best explains the experimental results? And we're like, oh, dang it, that didn't give me a lot of info. I guess I need to read the whole thing. Benzoic acid, okay, this HC7H5O, this guy right here. What is that? Well, it tells us it's an acid. I also can see that it's likely an acid because it has hydrogen at the front, but it's not one of my big six, so this must be a weak acid. Okay, so this weak acid, all right, has a pKa of 4.2 and a molar solubility of 0.0278 molar. They're trying to scare you. They're trying to confuse you. Let's just keep going. Sodium benzoate, NaC7H5O2. Oh wait, that should feel familiar. C7H5O2. So if I took this weak acid and I were to break it apart, like this H+, if that were to come off of this, then what we're left over with is the conjugate base, C7H5O2 minus. That's the conjugate base. Well, there's that conjugate base right there, C7H5O2 minus, and that's combined with Na. It must be a plus to go with that minus. This is an ionic salt. It's a metal with a group of nonmetals. Ionic salt that contains or with the conjugate acid. This is a buffer solution. We got a weak acid and we got a salt that contains, oh, I said conjugate acid, conjugate base, that contains the conjugate base. This is a buffer solution. Great. So there's our salt. Has a molar solubility of 4.16 molar. Several 50 milliliter samples of 2 molar sodium benzoate are treated with 3 molar HCl. Well, what is HCl? That's a strong acid. Okay, so we're adding a strong acid to the buffer solution. So let's think about this for a second. If we add a strong acid, first off, strong acids, they just break apart. So imagine it's just like a bunch of H+ floating around in there. Like that's what we added. Is that strong acid going to react with the acid, or is it going to react with the conjugate base? It's going to react with the base. C7H5O2 minus. And those will combine just to make more weak acid. Oops, HC7H5O2. Okay, so if we add a strong acid, it reacts with a conjugate base just to make more of that weak acid. So the pH changes a little bit, but it doesn't change a lot. Now, let's think about how do we think that this would change. Well, the first thing is if you add a strong acid, the pH probably goes down. So instead of the acid and the conjugate base having equal concentrations, what we get is we've added a strong acid, so I bet the pH is now lower than the pKa where they were equal before, right? So I think our pH is less than the pKa, so that narrowed us right there. And then here's the weak acid, and there's the salt that contains the conjugate base. We reacted with some of that conjugate base. So some of the base went away, and we made more acid. So there's now a little bit more acid, weak acid, than conjugate base. So the results would be the pH would be less than the pKa because there's more weak acid than there is base. And then it talks about a precipitate, but that's fine. It doesn't really matter. We don't need that info. So the answer is A. Okay. Let's look at these. An acetate buffer, oh, it tells us the buffer, that's nice, is prepared by combining 50 milliliters of 0.2 molar acetic acid. And so that's not one of the big 6 strong acids, so that's a weak acid. And 50 milliliters of 0.2 molar sodium acetate. And look, see the C2H3O2 and see the C2H3O2. This is a salt that has the conjugate base in it. So this is a buffer solution. 0.5 milliliter sample of 0.1 molar NaOH, sodium hydroxide, a strong base is added. Okay, strong base is added. Let's think about this. If we add a strong base, that just means that there's some OH minus floating around in there. And that strong base is not going to react with the conjugate base. It's going to react with the weak acid, this HC2H3O2. And the strong base is going to pull that hydrogen off of the acid to make water and leave us with more conjugate base. So, which of the following is a correct pairing for the acetate species present in greater concentration and the pH of the solution after the sodium hydroxide is added? If we add a base, then the pH will increase. So our pH should now be greater than the pKa. So it's either going to be B or D. Okay? And some of the weak acid went away and made more of the conjugate base. So this concentration of HC2H3O2, there's less of it now. There's less of it, and we have more of the conjugate base, C2H3O2 minus. And so which one is present in greater concentration? That would be this guy. So our answer is D. All right. Let's try one more of these. A solution is prepared by combining 1 liter of 0.5 molar HClO2. They're trying to trick us. HClO4, that's a strong acid, but this is a weak acid. With 1 liter of 0.5 molar KClO2. Oh, that's familiar. ClO2. ClO2. This is a salt with a conjugate base. This ClO2 minus and ClO2 minus. So this is a buffer solution. When 10 milliliters of 0.5 molar NaOH, when a strong base is added to the solution, the pH does not change significantly. That makes sense. It's a buffer solution. Which of the following is the net ionic equation? What's the equation for the reaction that occurs and prevents a significant change in pH? Well, if we have a strong base, then there's a whole bunch of OH minus floating around in there. And that's going to react with our weak acid, HClO2. And that base is going to pull that hydrogen off of there to make water, H2O, and it's going to leave behind our conjugate base. That's the reaction that's buffering against large changes in pH. And so our answer is D. When you read the questions, these sound scary, but they're not so bad. But the key to success is identifying. Identifying, is this a weak acid or a strong acid? Do we have the same conjugate base in there? So is this an ionic solid? Is it a metal with a group of nonmetals, or a metal and a nonmetal? And then what are we adding to this? Are we adding a base, or are we adding an acid? Okay. I think I'm gonna save. Let's see, PK. Sorry, last one, and then we'll save the rest for class. The table to the right shows values for Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equal amounts, results in a buffer with a pH closest to 7.5? Remember how at the half equivalence, the acid, when it has equal concentration to the conjugate base, then the pH equals the pKa. So if I go back to this, if they are in equal amounts, equal concentrations, then this pH should equal the pKa of that, 7.5. They just give us the Kas though, they don't give us the pKas. So we can get our calculators out and we can do the negative log of each of those to get the pKas, but we have a little trick here. Whatever the power is, if this is a 1, then the negative log of this would just be 4. But if there's a number here for the coefficient that's anything other than 1, then that just lowers your negative log answer just by a little bit. So this has a pKa that is a little bit less than 4. This one has a pKa that's a little bit less than 5. This one has a pKa that's a little bit less than 8. And this one has a pKa that's a little bit less than 10. So we want this guy, because see how its pKa is closest to that 7.5. So if I were to make a buffer solution, I would want that acid, the HClO, I would want that weak acid, and I need a salt that has the conjugate base. So if you break apart the H plus and then the ClO minus, there's our conjugate base. So I would want this acid with its conjugate base, and that buffer would have a pH close to 7.5, and it would resist changes in the pH. Okay, nice. I think we got it. So we will practice this in class.